Hey, Dr. Romano, what are you up to?
Hi, I'd like to show you a very challenging problem today on work and energy. Now, before I start the video, I want to make sure you understand a term which most students don't understand, and it's called mechanical energy. When I use the word mechanical energy, it's the kinetic and the potential together. Now, if there's no friction in a system, the mechanical energy at one point is equal to the mechanical energy at another point. So never forget that. If we compare 2 points, the mechanical energy at one, which is the sum of the kinetic and the potential, is the mechanical energy at the second point. If there's friction, then all bets are off the table, and that's not true. Let's take a look at a problem. Now, this is a very big university physics question. It could be anything you want it to be. Here, let's call it a box. A box is 200 grams, and it starts from rest. And it's up a distance of 4 meters. The surface is rough. Rough means it's got friction. And what we're going to do is we're going to slide the box down. And as you can see, it's going to move 10 meters. And it goes from point B to point C, and it's going to stop. Sometimes I see in physics books, this is disguised as a skier, skiing down a hill. When I used to ski with my best friend Georgette. And when me and Georgette used to ski, we used to start at the top of the mountain. We used to go all the way down, and then we would go, and then point C is the bar, and that's where we would end up stopping, and the rest of that don't worry about. Okay, let's do it. What I first want to do is to find the work of friction on the curve. Well, obviously, there is friction here. It's rough. So I can't say the mechanical at A is equal to the mechanical at B, but we're going to lose energy as we are moving from A to B. And that energy would come off as the work of friction. So I'm going to write this as the mechanical energy at A minus the work of friction equals the mechanical energy at B. The mechanical energy at A is the kinetic at A plus the potential at A minus the work of friction equals the mechanical at B, which is the kinetic energy at B plus the potential energy at B. It started from rest. Therefore, there's no kinetic energy at point A. We do have potential energy, which is mgh. There's the work of friction. When it gets to the bottom, there is no potential energy at B. There's no height. There's only kinetic, which is 1/2 mv squared. So we now get mgh minus the work of friction is 1/2 mv squared, and we do the plug-in. There's the mgh minus the work of friction is 1/2 times the mass. The velocity is 8, and we square it. I show you the work, and whoosh, we get the work of friction is 1.44 joules. Not so bad. Now, what is the coefficient of friction from B to C? Well, when I'm comparing B to C, I'm going to say that the mechanical energy at B minus the work of friction equals the mechanical energy at C. If there was no friction, then it would have just been mechanical at B equals the mechanical energy at C. We expand it out. Mechanical at B is the kinetic at B plus the potential at B. Now, be careful. The work of friction on a smooth surface, we're not on an angle, it's just on a smooth surface here or a flat surface, is equal to mg mu d. So that's a formula you should remember for work of friction. All right, that's equal to mechanical at C, which is the kinetic at C plus the potential at C. Well, at point C, it stops. So there's no kinetic at C, and we're on the ground, there's no potential. So all we have is the kinetic energy at B, 1/2 mv squared. We're on the ground, there's no height, so there's no potential at B, minus the mg mu d. I bring the mg mu d to the other side, cross out the masses, plug in the numbers, we know the velocity, we know g, we know the stopping distance, and whoosh, we get 0.326 for the coefficient of friction. It's a monster. That was a monster, but that's how you would do that type of a problem. You set it up, but always come through work energy theorem, where you're comparing the mechanical energy at one point with the mechanical energy at another point, and the problem becomes fairly straightforward.
Thank you, Dr. Romano. I'm going to say whoosh every time I'm working on this problem. What do you think of that?
Good day to you. I don't think much. Bye-bye.
Good day to you, sir. Wow, great problem.